Okay, welcome to mechatronics. Some mechatronics topics in we're doing quadrature encoder counting with the App Mega processor. I'm Professor Steve Canfield, your instructor for mechatronics. And this is the second part. In the first part of this video, let's jump over and look at our hardware. Oops. Jump over here and look at our hardware. In the first part of the video, we had this nice little setup here. We had our lovely turntable. We had a brushed DC motor with an encoder, although we're not really using that encoder. It had a 3-to-1 reduction, speed reduction, 3-to-1 torque amplification belt drive on the bottom that was driving this turntable here. At the moment, we're controlling the motor just through this DC power supply. I can increase the voltage, which proportionally increases the speed. I can slow it down, control the speed. I can control the direction by changing the polarity of the voltage drop across the motor here. So I got full control. And then there was an encoder on the bottom of this system. I don't want to mess anything up. Maybe I'll just pull this down. On the bottom, oops. Not, whew, definitely not a professional YouTuber. Oh, there we go, though. Do you see that? Right there on the top is the encoder. Right there's the encoder. It's actually a pass-through encoder. I'm not even focused in, but it's one of those US digital encoders. It actually has a hollow center, so the shaft runs up through it. The shaft goes underneath to this little belt drive, cute little belt drive there. There's an idler. There's the motor shaft. It's driving this guy. The encoder's in the middle, and the disc is on top. A whole bunch of washers. I'm not sure where those washers there. I guess just to take up space. The encoder leads coming out. There's 4 of them. The orange is power, brown is ground, yellow we're calling channel A, I think, or maybe channel B. Blue we're calling channel A. Get back focus. Thank you. This power supply here is powering the encoder. Notice it's taking right now. It's taking 23 milliamps, so very small voltage or small power required, which is what I expect. I've got my 2-channel oscilloscope connected. This is channel A. This is channel B. We saw previously that these 2 channels are out of phase right now. On a rising edge of channel A, channel B is high. Okay. If I go the other direction, flip directions here. On a rising edge of channel A, channel B is low. See that? We're going to use that little bit of interesting topic to determine which way our turntable is rotating. Okay, so without delay, let's go ahead and pull up our code. It's running. Oh, I just shut it down. Hold on, that was a mistake on my part. Okay, I shut it down and it disappeared. It took me a minute to find it. But here's the code we created on the previous. If you watch the previous video, we called it Quadrature Encoder with that Mega. We are connected channel A to interrupt 4, external interrupt 4, which is port E4, channel B on interrupt 5, port E5. We created a global variable we called encoder counts. And we set up the encoder external interrupt registers here. We printed the results to the screen and we're seeing the output. And if it's running right now, if we want to see what's happening, turn on the serial monitor. And there we're getting a current count starting out at 0. It's counting up. We saw, by the way, that counts were equal to degrees, 360 counts per rotation. So these are degrees. And I'm just tracking the position as a principal. But I'm not getting direction. Okay. So how do we get direction? We'll come over here. Right now we're only using channel A interrupt 4. That's the only one we're using. Channel 5 is 0. We're just ignoring it. So when I come in right now, every single time I increment encoder counts. But really what I want to do is I want to check channel B. If channel B, I guess if we call this the positive direction, if channel B is low, then I want to increment encoder counts if I want to call that forward. And if channel B is high, then I want to decrement. And you know what? This is going in a negative direction right now. So maybe we'll call this the negative direction and we'll call the other way the positive direction. So let's go ahead and do that. So I jump to my my code. And so rather than just blindly incrementing, I'm going to first check. So, you know, my check's going to look something like this. It's going to look something like if int int 5, or we'll say channel B is high, then increment encoder counts. And then I could say else, or I could say if channel B is low, I'm going to decrement encoder counts. Okay, so let's do it. So I'm going to say if now channel B that was on int 5, which was PE5. So I'm going to say if I'm going to read the state of pin E. I'm going to mask it, and I'm going to use an anding mask. I'm going to mask it with this. Well, I'm going to and it, I should say. I'm going to and it with this mask. I don't care about channel 5 or 7. Don't care about channel 6. I care about channel 5. Don't care about 4. Don't care about 3. Don't care about 2. Don't care about 1. Don't care about 0. So I'm going to and that thing with this guy. That's going to turn off every bit except for 1, for bit 1. So if it's high, this value is going to equal 0B 7, 6, 5, 4, 3, 2, 1, 0. Okay, so that in that case it's high. So I'm going to say I'm going to use this line right here. I've already created it. Okay, and if it's not high, in other words, if it's low, I'm going to do the same thing. So pin E ANDed with 0B 7, 6, 5, 4, 3, 2, 1, 0. This time I'd expect it to all be zeros. 1, 2, 3, 4, 5, 6, 7, 8. And in this case, I'm going to decrement encoder counts. Okay. And that's it. Okay. Now I could have used the else statement. Might have even been a little cleaner because in this case, you know, if the bits were coming in so fast that from the time that I did this first check, it went from say high then to low or vice versa. We're running a 16 megahertz processor. These if statements, a branch statement is going to take about 4 or 5 clock cycles. So I should be fine. I mean, that still should be sub microseconds. I should still be able to do all of these in 2 or 3 microseconds. And over here right now, if you looked on the screen, I'm on the order of milliseconds between these times. So I'm 3 orders of magnitude away. So at the moment, I think this is fine for the speeds that we're running at the moment. Okay, let's give this a try. So I'm compiling my sketch. And it's up here, up and running. Okay, so we're counting. Oops. Counting away in degrees. So now the truth in the pudding is I'm going to change my direction. So if you can see my arm in the background, I'm plugging the other direction. Now we're going in a positive direction. And is it counting down? It is not counting down. It is counting down. Yay. Okay, it's counting down. Now, the one thing I noticed is our signage is not quite right. I wanted this is a positive direction. Wait, see me there. This is a positive direction, but it's counting negatively. So do I care about that? Sure, why not? It doesn't take that much to change. So I'm going to just change the signs here. So there, that's counting down. That's counting up. And launch it again. So now I should be counting up in a positive direction, counting down in a negative direction. And so I'm counting up, counting down, counting back up. Okay, and look here, we've got the basis for control. Look at that. I could tell it go to 1,000, degrees and stop, or 10 degrees and stop. I have a little controller that's reading that, and it would keep track of it. Great. Okay, so now I've gotten encoder counting in degrees, and I've got direction control. Wonderful, wonderful. So thanks for your interest. Have fun. Happy mechatronics computing.